calculating and doing like GPS A, B, C for the first floor, and then starting
Nope.
GPS 1 with...
Oh, that could work.
yeah, GPS,
yeah. So,
GPS 1.
Yes, there was a question as to whether or not you can shortcut some of the code when you're only going to be working with a certain subset of items. So I think in your homework I asked you to do particular items, yes? Let me check this out here, because this may be a tip that other folks can benefit. So here's the list. So when you're writing your name statement at the very beginning, you can write all of these out and then just refer to this list. Or you can hack it. So you could do something like...
Could that be your use variable?
This is names to start. Let me get... So this is the idea, is what we're doing here, but when you type it out, what we can end up doing is be like GPS 1 through GPS 4. And then, because we want this to be number 1, you could call this like item 1. This one would be item 2. This is 3. There's no commas in here, by the way. It's just looks like this is item 4, item 5, item 6, and then you can go back to the rest of the list, right? Which would be number 11, I think, and so on. So that way, it doesn't know what they used to be called, and then you can refer to these as I1 to I8 in your code. The only trick is that if I ask you about specific items, you've got to back translate, like item 6 is now item 2, which may be more painful than just writing them all out. I'm not sure, but it can be handy to remember this. The M+ doesn't know what the variables used to be called. So you can save yourself some typing if you can shortcut them to things like I or V or however few letters it takes to make sure you know what you're talking about. So that was what we were talking about. Other questions? Really? Everyone's done, or is that easy? No one wants to talk? No. I have answered several questions about one. By the way, I absorbed 3 points into this, so this is an 18-point homework since it's so long. I figured that was fair, right? It's longer than usual. Number 31 and 34. So these calculations in terms of model fit get to be a little bit redundant. It's like, okay, fit it, it broke. Does it fit yet? No. Does it fit yet? No. Does it fit yet? No. And so I'm trying to change things up a little bit with number 31 and 34. Basically, the ideas are by how much are you heading in the right direction? Relative to your last index of how far off you are, how much closer are you now? So these ones are not just your typical results of your nested model comparison, but they require you to extrapolate between that model comparison and the one before it to figure out by how much have you reduced your chi-square for misfit. So several questions on that, but hopefully that makes it more clear. This one, I'm asking you to come up with only 2 significant digits after the decimal instead of 3. This is because in previous classes I had discovered that different operating systems yield different results for this homework. It has to do with the level of precision that M+'s floating numbers use, which apparently is an antiquated standard that is interpreted differently across different OSs. So rather than have a different answer as a function of which operating system you are using, which there's no way I could code for in the homework system, I just use 2 digits, and that seems to solve the problem. But if you get stuck and you think, I think this number should be right, I don't know what I did wrong, please tell me what you think it should be, and I can check against the answers and see how far off you are. So, all right. No questions? Really? Yeah, yes, sir?
So there was something in the first section of questions where you didn't answer, you didn't put 4 decimal places in the right?
Yes. That's, yeah, so your internal calculations. So M plus should give you 4 digits after the decimal for the scaling factors. I want you to use all 4 in doing your nested model comparisons, but the result of that comparison only has to be reported to 2 digits to be correct.
Yeah, I was mostly meaning when you're entering it into the homework.
Mm-hmm.
It was marking it correct or they're different. So if you use 3 decimal places for the correct values in the Excel table, you get the right decimal point.
Mm-hmm.
And then if you did 4, but I'll show you later.
Okay, okay.
They're registering 2 different ones.
Yes, so you might have the wrong scale factor when you enter it in, but then still have it be correct in terms of the calculations, or vice versa?
Yes, that's both.
Okay.
If you enter it as 3 digits,
Yeah.
okay, you'll get a p-value, and that p-value shows correct.
Uh-huh.
But then if you enter the test statistic for it, it shows as an incorrect. But then if you enter 4 digits into the Excel table, then the p-value is incorrect, but the test statistic is correct.
I'll have to look at that because I haven't come across that problem before. The way that I input the values is I input everything to the highest level precision I can and then just tell it to check against however many digits that is. So I don't round things or anything like that. So yeah, I'll have to, if you can show me after class or send me an example of what you mean, I can try to troubleshoot that. Okay. Others? All right, well, we have office hours after class if you're still working on that. Last quiz is out. That's due Wednesday. Revisions to homework 5, if you feel like doing them, are due Friday. And you should have all gotten a request from Qualtrics to do a survey. It told me they didn't bounce, so it went somewhere. It went to your emails or else your spam folders. Please take a look, and if you can't find it, let me know and I can resend. But you get 1 point extra credit for giving me some more specific feedback about your experience in this class. As I said before, it's anonymous. It knows which email addresses have completed surveys, but the answers are not tied to your email. So please be as open and honest as you can. So my microphone should be working. I forgot to charge it last time, and that's why it died, so my bad. But I never promised videos, right? I said I would try, and sometimes shit happens, and that's why this is not an online class. But I'm hopeful my microphone will last the whole time this time. So last time, then, we're talking about higher order factor models, yes? On our way to the big finale of SEM. So the logic behind these, in the same way that lower order factors, or what we've just been calling factors all semester, in the same way that lower order factors are supposed to predict the covariances between your items, the higher order factors are supposed to be able to predict the covariances between your factors. So higher order or structural models then is all about explaining factor covariances with 1 or more higher order factors. And just as we learned for measurement models, if you have 3 lower order factors, that's not enough to be able to test for the presence of a higher order factor. You'd be exchanging these 3 covariances for 3 factor loadings. That would look something like this, where we have a higher order factor now that predicts each lower order factor. Therefore, each lower order factor is now part the factor, the higher order factor, and part not the factor. We had a new vocabulary word for factor variance left over. Starts with a D. Disturbance, yes. Think of it as factor error, but it's error relative to higher order factor in this case. What do we need to be able to test a higher order factor? I'll take gestures. Hand gestures. 4. Yes, 4. All right, so then we looked at an example. Any questions on the example? Do I need to go back over any of that? We're fitting, I think, 6 lower order factors or 5? I can't remember. 5. 5 different ways to be mean to your children. Turned out that a higher order factor did not fit entirely the pattern of covariance, but it did for the most part. Here are some other examples of higher order factor models. I will pick up on slide 10 here. We'll look at a few of these, and then I have a lot of references on this topic for you that cite alternative work. So one of those, then, higher order factors. Another way that higher order factors or additional factors get put in is method factors. So if you're doing IFA and using full information maximum likelihood, you can't have error covariances. The alternative is to fit a method factor that accounts for that additional correlation. Here are different alternative structural models to deal with method effects and potential multidimensionality. So I like this article a lot, that's why I put it in here. I won't have the chance to talk about the random intercept too much, but I did want to point out a couple of options. So in this work, they're dealing with a 7-item scale about, we'll call it satisfaction with life. Some of them are positively worded and some of them are negatively worded. So the idea is that we should be measuring, if their theory is correct, the same trait with these 7 items, but we're measuring it differently with some than others. So they compared the fit of a couple alternative models and then introduced a 4th variant that was novel that would account for this type of situation. So here's one option. These are the 2 options that you guys know how to do already. Single factor. One way to handle the differences in how items correlate as a function of their direction, positive versus negative wording, or when items get reverse coded, is just to fit 2 factors. So that's one alternative. Here's the code that would go with each of these things. If you don't reverse code, then the covariance between these things would be negative. If you do reverse code, then these would be positive. So then we have a bifactor model. So several of you have asked questions about these models as they've come back into style recently. So bifactor doesn't mean 2. It's not like bicycle or biweekly. Bifactor is like bi, like split, like bisect, bifurcate. Any other bi words you know? I don't know. Split is the idea. So like this bifactor model has 3 factors. It's not 2. The idea is that each variable can have up to 2 sources of cause. One is the thing you think you're measuring, that you intended to measure, and something else that you didn't intend, but you nevertheless is relevant. So the way that this model handles the fact that items that are written the same way, positive or negative, are more correlated than expected is by introducing these specific factors down here. So this type of structure goes by a lot of different names. I would refer to those 2 bottom factors as method factors because it's the way you ask the question that is supposed to be accounted for by that circle. Bifactor model would also apply to this. Multi-trait, multi-method is when you have more than one trait at the top and it's measured more than one way. Like if you have 3 different constructs you're measuring and you ask both a parent and a child to report on the same thing, then you'd have multiple methods and multiple traits. But this type of structure has to be defended with the results, not just the structure, for it to be plausible. So in this case, it looks like the specific factor has really high loadings, more so than the original factor. That suggests that it's not just the positive wording. It's capturing more of the actual trait than the trait is capturing itself. So this neat interpretation of wording versus the thing I care about starts to break down to the extent that the loadings don't convey that story. In this case, we have the specific factors that follow this. They're much lower than the corresponding original factor loadings on the main factor. So it's hard to argue that this is overall optimism when it's really more pessimism or lack of pessimism based on the factor loadings. So these bifactor type models tend to be used whenever you have something you care about, and that's the general factor, and then there's like this crap left over. There's wording, or there's these extra things that are causing this extra source of correlation that you just want to control for and not make a big deal of. So in this case, one might only pay attention to the factor scores for the general factor and not do anything else with these method factors other than let them just exist to soak up that extra correlation. I have one example of a type of model that I've fit with this. So here's his version of the random intercept factor model, and he concludes that it works well for these data. Here's a real-world problem that I had to grapple with when I barely knew what I was doing. As you can tell, this is from a paper published in 2005, so this is shortly after I got out of grad school. This is the Heartland forgiveness scale developed at KU, in fact. And I've told you a story about this before. We've looked at this little chunk of it, situation factor. Well, these are the others. So there's 6 items that measure self-forgiveness, 6 items that measure other forgiveness, 6 items that measure situation. And for each of these subscales, 3 are positively worded and 3 are negatively worded. Well, no matter what I did, this was the factor structure that I had to start with. The items that measured the same thing in the same way always wanted to be more correlated than anything else. So I started with 6 lower order factors. Now, how do I get the intended 3 subscales of forgiveness, of self, other, situation out of that? This. So let's go over this, because one might call this a bifactor model. One might call this a multi-trait, multi-method model. In this case, the idea is that these 5 new factors are being introduced to predict the covariances among the 6 lower order factors. So I have eliminated the measurement model portion from the picture just to focus on the structural portion, and the numbers in parentheses go with their corresponding constraints in the M+ code. So my version of this is that I wanted to say, well, the items that measure self should go onto a self factor. The items that measure other should go onto an other factor. The items that measure situation should go onto a situation factor. Seems reasonable. However, I've only got 2 of each. So to make these things identified, I have to constrain loadings. But I did so in an atypical fashion that I thought made more sense. Rather than saying that positively worded items and negatively worded items have to have the same contribution to the higher order factor, I said that their contribution has to be equal across factors. So the extent to which positive and negative measure each of their traits is being held constant across the traits. So I'm not allowing any sort of confound that certain traits are measured better by positive or better than negative. I'm holding it equal. On the other side, to handle the patterns introduced because items that are positively worded are more related than expected, despite even what they're about, I introduced what I would call method factors. So the red one there has a set of loadings that's constrained. Because if it really is just about being a positively worded item, then there's no reason for any differences across self, other, or situation, because they're all positively worded to the same extent. So I operationalized that claim by holding all of those loadings constant and holding all of the loadings constant across the negative. So I'm not allowing problematic interpretation in terms of the method factors being more meaningful or capturing more of the variance than the construct factors, because I'm setting up these constraints to do it this way. And so you can see in here then, we have the positive factors, the negative factors. We have the covariances among the content factors, but there cannot be covariances on the method side or it's not identified. Positive wording factor and negative wording factor cannot have a covariance. The reason that they would have been related is this thing people are reporting about, which is on the right-hand side of the model instead. So we have to keep those separate. So you can think of these as residual covariances. They are just being introduced to allow an extra pattern of covariance among the positives and among the negatives. They are set to have no covariances with each other or with this other side of the model. I then also constrain the factor disturbances to be constant for the positive factor and for the negative factor, although they got to vary between the two of them. So in the original paper, which I had tried to explain all of this model fits well. Yay me! Yay me? How do I know that it fits well? In the paper, I'm all, CFI is good, RMSEA is good, it's fine. See? What is the proper test of whether or not this convoluted 5-factor higher order thingy actually describes the pattern of covariance among the lower order factors? Not worse than what? Not worse, that's right. But not worse than what? What's my benchmark? What's the best I can have for my structural model? Yep. Covariances between all the factors. So this is my cheaty way of describing that. Having the arrows connect to each other and go in, this is my way of saying all possible covariances. Makes the diagram neater. I think it still works to convey it. So yeah, this should have been the best fitting model, and that pattern of covariance should have then been predicted by these things. Did I do that? No. I didn't know that at the time. My bad. So don't be like me. So that would have been the proper test of that hypothesis. But since this fit well, I decided to go with it. Now, I did get reviewer 3 come back and say, no, you got the labels on these circles wrong. This measures forgiveness, that's what positive means, and negative means unforgiveness. And over here on the right, those are your method factors. There's 3 ways of measuring forgiveness. Exactly. Okay. Now, do I ever really know what's in my circles? No. Circles are just piles of covariance that we've given a name to. Whether or not we're measuring what we think we are is a validity question, answerable by how these circles then relate to other things. But I could argue that the constraints that I've put on this make my interpretation the right one. So to address reviewer 3, and this was in the manuscript, I flipped the constraints around. Said, okay, if you're right, then all of the loading should get to be whatever they want on the forgiveness and unforgiveness factors on the left side. And all of these method factors should be able to be held equal, because it doesn't matter how I measured it, right? We're just addressing extra covariance because of method. And that model was non-nested relative to the other model. How do I address reviewer 3? How do I compare non-nested models? How do you do it in any stats class that you've ever had for me or anyone else, where you're talking about maximum likelihood? You know you want to say it, Lucas. Heather, you should say it. Let's see. Non-nested models? Yes, you can. Yes, you can. Yes, sir? Yes, AIC and BIC. And so AIC and BIC, lower is better. And I got to write back, Dear Reviewer 3, Thank you for your interesting alternative explanation. As now addressed on page whatever, you're wrong, suck it. So yeah. So these models, it becomes trickier and trickier to say what's what. But I would encourage you to try to phrase your expectations and your hypotheses in ways that are disconfirmable by the data, such as these types of additional constraints. So technically speaking, I think these factors out here could be considered random intercept factors the same way as in the first paper that I mentioned, because they're just an extra constant source of covariance among the factors that are all measured the same way. So you can think of it that way. All right. Questions on that? Okay. So here is a very simple picture meant to illustrate a very big idea that I really hope you guys take with you, and so you're never the person that I'm about to mock. Not me this time. Although I've made plenty of mistakes in print. The idea that these models, path models, structural equation models, are causal models. You've heard of this, right? Causal modeling is what it's called. Doesn't that sound nice? Like that's the way we can finally answer all these questions? No. What we have is a covariance matrix and a way of predicting it. That's it. There's nothing causal about it. So here are two very different theoretical models, 3 variables. So models with only observed variables are called path models. Models that also have latent factors are called structural equation models. But in the model on the left, A causes B and B causes C. The model says the only reason that A and C are related is through B. So this would be a classic mediation model where the A times B path and the B times C path would be, those two paths multiplied together would be known as an indirect effect. The model on the right is completely different. No. C causes B, which then causes A. And the only reason that C and A are related is through B. So let's say that you put the model on the left side in your dissertation, and the methods expert on your committee says, well, do you think the model, I think the model would fit better if you did it this way. This happened. This has happened more than once, I'm afraid. And I sat there going, please get this right. Please get this right. The correct answer? Dear well-meaning committee member, these two models fit the same. They fit the same. On the basis of fit, there is no way to differentiate them. Remember what fit is and what fit isn't. Fit means the model you've specified accurately describes the patterns of relationships in your data. So both models allow B and C to be related. Both models allow B and A to be related. And both models say that the only reason for A to C is B, or C to A is B. So I could have arrows going one way, arrows going the other way, or just covariances. They all fit the same. There is no way in observational cross-sectional data to use these models to attribute cause. There's not. The model will not fit better if you reverse the arrows. Here's an example of this same phenomenon in the context of latent variable modeling. Let's say that we think of depression as being causing 4 observed responses, 4 indicators. That's the picture on the top right. Someone else comes along and says, no. No, item 1 is what causes depression, and depression then causes your answers to those other 3 things. And then someone else comes along, no, item 3 causes depression. These are all the same. They all fit the same. because fit is about reproducing relationships between observed variables. So if I go, what is the relationship between item 1 and item 3? It's this path times that path. What is the relationship between item 1 and item 3? This path times that path. All of these models are going to fit the same, even if they have different interpretations. So, it can be tricky to figure out what's the same and what's not the same, but those are some basic cases. If you fit a model and then you fit a different model and it has the same degrees of freedom, they may be equivalent. Question?
On the previous slide,
Yeah.
so there's still a theoretical problem with having one observed variable predicting a factor, right? There's still a theoretical problem with that. There's statistically, there's not going to be any difference.
These models fit equivalently. So the ones on the right, or the left, excuse me, are thinking of one of those variables as the predictor and depression is the outcome.
And there's still the downside of just having a single item.
Yeah, well, I mean, you could think of that as a subscale instead. But the premise is that these models all specify the same pattern of covariance among these 4 boxes. So you can't use fit to decide which one is right. The only time I've ever been in a position of being able to successfully argue as to which came first is when I had something like the left side, and a reviewer 3 said, how do you know that this one should be the effect and this one should be the predictor? And fortunately, in that situation, I was able to say, because the thing on the right happened 5 years later, I win. There's no way that you can cause the past, I'm pretty sure.